Hello and welcome to part 10 of Dev Maths and Stats Refresher Course, Lecture 5. And now we come to the first order conditions with equality constraints using the Lagrangian method. So the previous stuff was about why this works. Now this is how you apply it in practice. So we want to optimize this function subject to this condition. The method is you make a new function which is called the Lagrangian. L, which depends on x and y, the original variables, plus a new variable that you introduce, which is this number lambda, the Greek letter. So Lagrangian of x, y, lambda, function of three variables, is equal to the original function plus lambda times, and then in brackets, the value of the constraint minus the constraint. So in a sense, this is like lambda times what you've got left before you reach the constraint, so C minus the constraint. And the first order conditions are simply that, as usual, as though this was an ordinary function you were trying to optimize without constraints. All of the first derivatives have to be 0. And you should be able to see that the first two of these conditions give the same result as in A above. So if you differentiate this with respect to x, you find that f of x minus lambda times gx, so partial derivative with respect to x here, minus lambda times partial derivative with respect to g of x is equal to 0. In other words, that gives you this first condition. And then the next one, differentiate with respect to y, you get this condition straight away. And then when you differentiate with respect to lambda, you just get that c must equal g, which is the constraint. So it just very neatly summarizes those three conditions. Okay, so do some examples of this. Before I do the one above, which is quite complicated, I'll just do a simple one, the kind of thing that you're more likely to meet on problem sheets and so on. So let's maximize this subject to this constraint, so it's a linear constraint. So first of all, define the objective function, and you notice that the code is again and again the same in Maple because it's just doing the same thing. It's kind of routine. So objective function, the constraint, and the value of the constraint. Then set up the Lagrangian function. You have to use this awkward command, but that's just technical in Maple. So there's the Lagrangian. So can you see what we've got? We've got, it's the original function plus lambda times the value of the constraint minus the constraint. And then you should be able to do the first order condition, which is just partial derivatives with respect to all three variables there. So we differentiate that with respect to x and y and lambda, you get this. And here, it's just because you have a nice set of three equations and three variables, they're all linear, so you can use inverse matrix or Cramer's method. I use Cramer's one just because it's neat to write out on the computer. So that's the coefficients from this. So you've got the x coefficient, the y, and the lambda. And then b is when you move the constants to the right. So it's the minus 10. This one's a 0. This one's a minus 8 on the right here. And then you need, as well as this matrix, you need the extra matrices when you put the right-hand side into this column, this column, this column. So you know there's an easy way of doing that, writing it in Maple. Okay. And then the solutions to those simultaneous equations just drop out this determinant divided by the original determinant, and then this one, and so on. So it's each of those special matrices determinants divided by the original determinant gives you the x and y and lambda. Okay, so there's your optimum, 25/7, so a little bit over 3, and a little bit under 1 for y. That's the value of lambda, which at the moment doesn't mean anything. You should calculate the value of the optimum point by putting in these two. So it comes out about 25. Okay. And to see if it's correct, if you draw a graph of this, the graph is saying that you're going to find at the point 3 and a bit, and just under 1, you get something with a solution of about 25. So x is just over 3, y is just under 1, so that's here. And the solution comes out as about 25, which is hopefully convincing if you manage to get it straight. So the solution is about 25, and it's indeed at the points just under 1 and just around 3 for x. So it's worked. Okay, this lambda is really only used as a mechanism for getting to that solution, but it does actually have a meaning in itself. What happens if we work through the whole problem again, but with 2x plus y equals a 9 instead of 2x plus y equals 8? So, for example, this is you're using some resources. Instead of 8 units of resources, you have 9 units now. So now, what happens if you repeat the whole thing? What happens is this. So, the black one is the original solution, but now with the extra units I've got, instead of whatever it was, 2x plus y being equal to 8, it now can be equal to 9. So now, instead of this being the highest point I can reach, I can now reach this point here. And you can see that relaxing that constraint by 1 unit from 8 to 9 increases the maximum value of fxy you can find, that you can get. And in fact, it turns out that lambda gives you the linear estimate of how much that increases by. It's actually the derivative of the increase of the maximum every time you increase the constraint. So the partial derivative of the maximum by the constraint. So like this. That's the meaning of lambda. Finally, before we finish, let's just go to the one that I started with. Started this part of the lecture, where it's more complicated. Drawing because we've got this complicated constraint function. I just did this because it looks more interesting. So you should be able to do this, form the lambda. So lambda is the original function plus lambda times this minus this. So the paper was written a bit ugly. Then derivatives with respect to x and y and lambda, you should be able to follow that. It's the slightly hard bit. It does take at least 2 pages of fiddly calculation, which I'm not going to do on the whiteboard to get to this. It's very unpleasant, so I would not even think about giving you this in any test. And indeed, for practical work, you would be just solve it on a computer. But it is possible. So these are the solutions. So, where's the evaluation of the solutions? Okay, so that's lambda. So substitute that back in, solve. Okay, so you get 13 and 26. And then substitute those values back into the original function. And you get 117. So minimum value of f is about 117 at the points 13, 26. So is that at all convincing? Where is it? So I have to remember that. 13, 26 and 117. Yeah, so x is 13, y is 26, yeah, indeed there. So there's the 26, there's the 13, so it takes you to this point. And if you look at levels wise, yeah, 117 looks pretty convincing, pretty better on this one. Yeah. Right, well, yeah, that's the 117. Okay, so it does, it's harder to solve the equation because it's not linear, but if you do work through it, you do get something which is correct. Okay, so in the final part of this lecture, we'll move on from this to look at the situation where we have inequality constraints, optimization with inequality constraints. But for now, thanks for watching.